If we think about an electron moving, we think about a possible path. For example, let's say a pitcher throwing a baseball. All right, we've got a trajectory there. That's a single line trajectory. All right, that's because we can see the baseball, we can measure it where it started, where it ended at, and that's fine. The problem is, since we can't measure an electron, we don't know exactly the path it typically takes. All we know is that it's somewhere in the atom and it's moving around between these energy levels. The best we can do is come up with something called a probability distribution map. Probability distribution map is going to show us the most probable location that an electron would be at. All right, so let's say I have 1,000 baseballs thrown, and they all end up getting over the plate at some point, but when they end up over the plate, they end up in different spots. Right? They don't always end in the exact same spot. They follow the same basic trajectory, but there's a probability that any given baseball could be thrown in such a way as to hit in the different regions of the strike zone there. So if we wanted to predict the next given baseball where it's thrown and the path it's going to follow, we'd have this probability map. Well, the same thing is going to be done with electrons to figure out where these electrons are at in these atoms. But to do that, we're going to use something called a wave function. Now, wave function is going to be represented by a psi. It's going to be related to these atomic orbitals, these energy levels within the atom. All right, and then we're going to do something with those wave functions to create something called a probability density. Okay, and it's listed as psi squared. You don't need to know the equations for those, but you do need to know what they represent. In this case, probability density is going to represent where is the most probable location of us finding an electron in a certain energy level, a certain distance from the nucleus. Okay, so within that energy level, what's all the possibilities of where we can find the electron? That's what we're looking at with these probability densities, because we can never know exactly where an electron is at any given moment. And the probability density is just going to be a mathematical formula that's going to generate this map of where all the possible probable locations of the electron are. Now, a simplified way of viewing these mathematical equations is going to be something called quantum numbers. Quantum numbers are going to be a way for us to detail where an electron's at in any given atom. Okay, it's going to basically give us a way to map out where these electrons are at. Just like when we need to map out something in 3D space, we have an X, Y, Z coordinate system. That's what the quantum numbers are going to help us with, is to describe where an electron's at in a coordinate system. So we have to understand these quantum numbers. All right, first quantum number we need to know is something called a principal quantum number. We've actually seen this before. Principal quantum number, it's represented by n. N can be 1, 2, 3, 4, 5, and so on. We've already talked about that when we talked about those different energy levels surrounding the nucleus. So we're going to consider these as kind of shells around the nucleus. As we go to higher and higher principal quantum numbers, we get to larger and larger shells as we go further and further out from the nucleus. Okay, and all of these are kind of on top of each other. All right, the next quantum number we need to know is something called the secondary quantum number. It's represented by an L. L values are going to start at 0 and are going to go up to a value of n minus 1 by integers of 1. So L values are going to be dependent upon what n you're starting with. So if n equals 1, L can only be 0. If n equals 2, L could be 0 or 1. If n equals 3, it could be 0, 1, or 2. So it starts at 0, goes up to a value of n minus 1 by integers of 1. Now what this secondary quantum number is going to tell us, it's going to tell us the name of the subshell. Right, the name of the subshell is going to help us predict shapes of these probability densities and shapes of these orbitals that we're going to use to help us build models of what these atoms look like, what the compounds look like that are made up from these atoms. Now, because it's going to give us the name of the subshell, we need to know what that name is. So if I have an L value of 0, the name of the subshell is going to be S, or an S orbital. If I have an L value of 1, it's going to be P. L value 2, it's going to be D. L value 3, it's going to be F. Okay, so these L values are going to tell us the name of the subshell. It's going to tell us the name of the orbital that we're dealing with, where this electron is located at. All right, next one. It's going to be something called the magnetic quantum number, m sub L. M sub L can range from positive L to negative L. All right, what m sub L tells us, it tells us the number of atomic orbitals in a subshell. Okay, so L gives us the name of those orbitals. M sub L gives us the number of those orbitals. So let's look at this. Well, if I have an L value of 0, the name of the subshell is S, the number of orbitals in that subshell is going to be 1 orbital. Why? Well, if L is 0, then M sub L can only be 0. Right? Positive L to negative L, well, it's only 0, so we only have 1 orbital. What about when L equals 1? Well, that's a P subshell. It's going to have 3 orbitals. Why 3 orbitals? Well, because M sub L could be plus 1, 0, minus 1. L equals 2, that's a D subshell. D subshell is going to have 5 orbitals in it. So plus 2, plus 1, 0, minus 1, minus 2. There's 5 different numbers that we could set up there. If L equals 3, it's going to be an F subshell. There's going to be 7 possibilities there. Plus 3, plus 2, plus 1, 0, minus 1, minus 2, minus 3. Okay, there's 7 M sub L values there. Okay, so M sub L tells us the number of atomic orbitals. And the last quantum number we have to worry about is something called the electron spin number, M sub S. Well, M sub S can either be plus 1/2 or minus 1/2. So when we're dealing with the plus 1/2, minus 1/2, this is talking about the spin of an electron. An electron is a charged particle, and it's spinning. If a charged particle spins, it's going to have a magnetic moment in a certain direction. Okay? That direction is going to be dependent upon whether it's spinning clockwise or whether it's spinning counterclockwise. So we designate those 2 different types of spin as spin up, the plus 1/2, and spin down, the minus 1/2. So when we put these all together, if I have the principal quantum number n equals 1, then I can only have L equal to 0, which is an S orbital. Then I can only have L equals 0, which is an S subshell. Within that S subshell, I can only have 1 orbital, because M sub L can only be 0. Within that orbital, then, I can have 2 electrons. One could be spin up, one could be spin down. N equals 2, I could have an S or a P sublevel, depending upon whether my L is 0 or my L is 1. If my L is 0, I've got the S subshell. I can only have 1 orbital in that, which means I'd have 2 electrons, spin up, spin down. If it's the P subshell, L equals 1, my M sub L could be minus 1, 0, plus 1, which means I could have 3 orbitals. Each orbital can contain 2 electrons, so I could have a total of 6 electrons there. Okay? And then the third level is shown there as well. All right? This is another kind of table of all of those things where you're looking at n equals 1, 2, 3, and 4, and all the possibilities there. Something we need to mention, though, when we're looking at this, we need to worry about something called the Pauli exclusion principle. Basically, what the Pauli exclusion principle states is that you can't have 2 electrons that have the same set of quantum numbers. Remember, these quantum numbers are our coordinate system to describe where electrons are at in an atom. So we can't have electrons have the same quantum numbers because that means they exist in the same space. It'd be like giving the coordinate system XYZ coordinate system for 2 different objects as having the same XYZ coordinate system. That means they're occupying the exact same space, and they can't do that. Every single electron in an atom gets its individual set of quantum numbers. We can never have overlapping quantum numbers. Okay, so let's run through assigning some of these quantum numbers. So if I have n equals 2, what are the possible values of L? Well, L could be 0 or 1. Okay, 0 represents S, 1 represents P subshell. What if I have an L value of 2? What possible values of M sub L could I have? Well, first, if L equals 2, what subshell do I have? Well, it's D. Okay, it's a D subshell. As far as the values of M sub L, minus 2, minus 1, 0, plus 1, plus 2. All right, if M sub L equals 0, what are the possible values of M sub S? Well, M sub S is always going to be plus 1/2 or minus 1/2. Let's look at a slightly different example. Let's say I have a 3p orbital and I want to know what quantum numbers are possible for that 3p orbital. How do I pull that information out? The 3 tells me I'm in the 3 shell, n equals 3. The p tells me I'm dealing with an L value of 1 because 1 represents that p subshell designation. If L equals 1, M sub L could be a minus 1, 0, or a plus 1. M sub S then could be a plus 1/2 or a minus 1/2. Now let's actually write out a set of quantum numbers for 3 specific electrons in the 4D subshell. Well, first I need to figure out what are the possible quantum numbers I could have. Well, I've got 4D, so n equals 4. Got the D subshell, so L equals 2. If If L equals 2, my m sub L could be minus 2, minus 1, 0, plus 1, plus 2. My m sub S is always the plus 1/2, minus 1/2. So keeping those values in mind, we're now going to look at how we can assign quantum numbers to specific electrons. All right, so now that I know the sets of quantum numbers I have to choose from, let's get even more specific to those 3 specific electrons. So if I look at this representation here, each one of those lines represents an orbital. Each arrow represents an electron. So an arrow pointing up represents a spin-up electron. Arrow pointing down represents a spin-down electron. And then I have my m sub L values listed out there. And those m sub L values tell me how many orbitals or how many lines I have. Okay, now when I report out my quantum numbers, I'm going to write them in parentheses, and I'm going to have my n, then my L, then my m sub L, then my m sub S value. I've got all the possible electrons I could have up there. Notice each orbital gets one spin up, one spin down. Okay, so let's just pick one of them. So I'm going to take this electron right here and write out the quantum numbers for it. So for those quantum numbers, my n value would be 4. Why? Well, because those are all 4d orbitals, so n equals 4 for those. My L value would be 2. Why? Well, because they're in the d subshell, so L equals 2. My m sub L value would be minus 2. Why? Well, because I've designated that particular orbital as a minus 2 for my m sub L value. And then my m sub S would be a plus 1/2. Why? Well, because it's a spin-up electron. The electron right next to it would be 4, 2, minus 2, minus 1/2, because it's a spin down, but it's in the same orbital. All right, so each one of those electrons would get its own individual set of quantum numbers, which wouldn't violate the Pauli exclusion principle. But we couldn't have 2 electrons both in spin up or spin down in the same orbital. Let's look at another one here. Let's take this electron, assign its numbers. So it's going to be 4, 2, 0, plus 1/2. Notice the 4 and the 2 are the same. Why? Well, because these are all 4d orbitals. So n equals 4, L equals 2. All right, let's pick a third one out here. Let's take this one. So that would be 4, 2, plus 1/2, minus 1/2. So I said before, these quantum numbers are ways of us assigning location of electrons within an atom. It's like our XYZ coordinate system, except now we have this NL, M sub L, M sub S. Okay? Every single electron in an atom has to have a different set of quantum numbers. They have the same set of quantum numbers. They're technically listed as occupying the same space then, and we can't have that. So that's assigning quantum numbers. Now, where do these quantum numbers come up? Remember, we talked about those probability densities and how we use those quantum numbers to get these wave functions, to get this probability density, to help us describe where an electron is in an atom. So we've got those quantum numbers. Let's look a little bit more at these probability densities. Those probability densities are going to help us get shapes of these orbitals. All right, so we could look at an s orbital and look at probability densities. And remember, these are probability densities. The electron could be inside this shape anywhere at any given moment. Okay, this is not the shape of an electron. It's just where's the greatest likelihood of having an electron exist. If we could freeze that atom and find the electron, it's somewhere within this shape if we're dealing with an s orbital. Okay, so an s orbital, then you've got this little spinning picture here. It's going to be spherical. All right, that's what an s orbital is. So when we think about shapes of s orbitals, they're just these spheres. As we go to higher and higher n values, those spheres get bigger. Remember, n equals 2 is outside n equals 1. So n equals 1 has to be inside n equals 2. Then n equals 1 and 2 have to be inside n equals 3, and so on. Okay, it's that building up of those shells. So as we go to higher n values, the size of these orbitals get bigger. Okay, let's look at p orbitals. Well, with the probability of a p orbital, the way that mathematical probability calculation works out, it ends up creating this dumbbell shape where we've got 2 lobes. All right, so a p orbital looks like this dumbbell, and we're going to have 3 p orbitals. Why are we going to have 3 p orbitals? Well, if we have a p orbital, L is equal to what? It's equal to 1, which means m sub L is equal to minus 1, 0, plus 1, which means we have 3 p orbitals. These are the 3 different p orbitals. We designate them as p sub z, p sub x, p sub y, depending upon which axis of the xyz coordinate system that orbital falls on. Now when we look at them all together in a specific subshell involving that p orbitals, they overlap in that bottom picture there. Okay, but when we think about a p orbital, it's just this dumbbell shape. And depending upon which axis that dumbbell is on, determines whether we're dealing with the px, the py, the pz. Now, when we go to the d orbitals, they get a little bit more complicated in terms of their structure. Right, but basically, majority of them have this cloverleaf picture, okay, where they've got 4 lobes set in different planes. Right, these are representative of the d orbitals. Now, keep in mind with d orbitals, if I have a d orbital, my L is equal to 2, my m sub L would be minus 2, minus 1, 0, plus 1, plus 2, which means I'm going to have 5 different types of d orbitals. Well, those 5 different types in this picture are starting with d and going to h. So d, e, f, g, h are the 5 different types of d orbitals and their structures. Okay, the first 4 you can see are that cloverleaf shape, right? It just depends on what plane they're in. So dyz, those 4 cloverleafs are in the plane of yz. Notice none of them are falling on any axes lines, they're in between axes. Okay, dxz is in the plane of xz, dxy is in the plane of xy. When we go to the dx squared minus y squared, though, those are on the axes lines. The lobes are actually on the lines now, and it's in the plane of x and y. Okay, that's the dx squared minus y squared. When we get to the dz squared, it looks a little bit goofy. What we typically say with that is if you're to picture that central part as a donut, and we put a p orbital through that donut, that would be a representative of the dz squared. So d, e, f, g, and h, those are the representations of the d orbitals. Those are what the shapes of those d orbitals we'd expect to look like. Those are the shapes of the probability densities of those d orbitals. Okay, I then just shows them, if we throw them all together as overlapping, which technically they all are there, you can see all the different types of overlap, and you can see those lobes going off in all different directions. Okay, but we're only concerned, if you need to draw these, we're only concerned with single orbitals. Right, just some pictures of this then. So the dx squared minus y squared orbital, you can see the 4 different lobes there as it rotates around the z-axis. Okay, and the dz squared, this picture probably shows you a little bit better what I mentioned. If you take a donut and put a p orbital through the middle of that donut, that's the dz squared orbital. That's going to take us to the end of these orbitals in this quantum theory. Right, you need to be able to assign quantum numbers. You need to be able to identify where these electrons are at in a given atom based upon those quantum numbers. You then need to understand those probability densities and be able to draw the different shapes associated with those different orbital types. And you're going to need to be able to draw the shapes of those probability densities associated with those different types of orbitals. We didn't go into f orbital shapes, but there are probability densities for f orbitals as well. It's just those shapes are more difficult to draw. All right, but that's going to take us to the end of quantum theory and quantum numbers.